All right, so this section is on vector fields, and the gradient is an example of a vector field, something you've encountered before back in Calc 2. We didn't call it that then, but let's just jump into an example. Okay, so vector fields. A vector field it's just a vector value function, vector value function. Sometimes the field is itself, considered the function, the graph, and sometimes it's the function, but the idea is that you have a function of more than one variable, usually, right? And that function goes into a vector, which is then of more than one variable as well, so I'll write it like this. Right, so you bring in two variables, and then you spit out a vector in 2 dimensions. Does that make sense? So for every point in space, there's a corresponding vector to that point. So that's where this idea of a vector field comes in. So let's just look at an example. Sketch the vector field for, let's just do capital F of x, y equal to, let's just do this at x minus y, and then 2y. And I'm going to be a little bit lazy because we'll see why this is a pain in a second. On negative 2, 2. So, this probably doesn't have enough information to really do this problem in its entirety, and that's okay. I'm not going to ask you to do this. So vector fields turn out to be things that you don't want to sketch by hand ever. It's kind of silly to sketch it by hand. There's a lot of things. Right? Remember slope fields when, I guess, it depends on what you covered in Calc 2. If you've had differential equations, you've seen slope fields. Maybe you did in Calc 2, but it's another place where you don't want to do everything, to drive everything. So here's the idea. Right, we're going from negative 2 to 2. Actually, our field might get bigger than that. Let me just put them here. Negative 2 to 2. Negative 2 to 2. Okay. And so the idea is that at each point in space, these guys correspond to vectors, right? The f of whatever. And so let's just pick some random points. So take the origin. Plug in 0, 0, what do you get?
X equals to y, y equals to 0.
Well, you're just plugging in 0 and 0 for x and y. So 0 minus 0.
Oh.
Is that, you're not setting them equal to 0. You're just saying 0 minus 0, comma, 2 times 0. So 0, 0. So that's a trivial vector, right? So I won't draw it. Let's move over a little bit. What if we're at the point 1, 0?
1, 0.
So that's here, right? And then what's your 1, 0? So that means we get this vector that looks like that. Does that make sense? You get the vector from your starting point, from 1, 0. You have a vector pointing one more unit. What about f of 0, 1? I'm just going to write a couple down. F of that should be good enough. So draw the corresponding vectors. So you're putting their starting point at whatever your base point was here, right? And then you draw the corresponding. Maybe here, let's do one more. F of 2, 2. We'll go in that upper right corner as well. Is that what you guys got for all of those? Speak up if you see something else. So at 0, 1, so that means we're at 0, 1, right? What vector are we getting? Negative x, 2y. So that means we go 1 unit this way and 2 units up. So we get that vector there. Does that make sense? Okay, at 1, 1, so that's here. We get the vector that goes no units in the x direction, right? And just 2 units straight up. So you get a vector like that. Does that make sense? How about at negative 1, 1, negative 1, 1, we go 2 units to the left and 2 units up, right? So we go back. Okay. Again, I'm not worried about being perfect on scale there. Things. And finally at 2, 2, so if we're up at this point here, we just go straight up. Oh, that should be more than that. Okay. So up on the wall a little bit. Okay. So hopefully this is enough to convince you that drawing these by hand is silly, right? You could theoretically go to every point and draw in the vector that corresponds with it, but the idea is to program or to punch this into some program and give you that visualization of what's going on for this. That'll be the important thing. The important thing to look at. And I'll say that when we plug it into a computer, we don't generally get the vectors of the exact length there. We get a scaling of them so that we can fit them all on the same screen. The bigger ones, right, will be bigger. So if this is only 1 unit long, it'll be half of one that's 2 units long. But everything's scaled down, so you just have arrows sort of with a relative scale. So you know where you have a big change and where you have a sort of small change. Okay? And here, let's just do one of these examples that we always do, these recognize the vector example. Recognize the function. There we go. Do a couple things here. All right, so next time, hopefully, Mathematica will be working again and we can pull up some and do some manipulations with some actual examples. But the book has some decent pictures we can. Colin, as you can see, this is a really long section. So here's basically what we just did, right, with a couple examples. So they give you some examples. You could do the exact same thing with a function in three-dimensional space, right? You could have x, y, and z be given, and then you're given a vector valued function in x, y, and z. And so you got a point in 3 space, and then a vector in 3 space. And so you should be able to sketch that, and that's here. Now that gets really hard to do by hand, right? Getting arrows pointing in the right place in 3 space. Not at all what I'm expecting you to do by hand, but we want to sort of be able to read information off of these guys. And so here they give a nice example, which is kind of like what we just did. So 2y, negative 2x over that same square. And so they're just getting a bunch of points here, showing you the vectors like we did, right? And then that's the sketch of the vectors here that they found. And then they went ahead and sketched a ton more vectors, right? And so this is with the actual lengths of the vectors that should be there. And you can see that becomes really hard to read, right? And so that's what I was mentioning. We're going to take these things and just scale the vectors down, and then you get this vector field instead, right? And so you can see there's a nice sort of rotation going on in those arrows, right? And so those are the kind of things we're going to look for as we move ahead. Okay? And then same thing in the 3D space. The point is you can scale everything down. You know, there might be a couple examples that say sketch them by hand in the homework. I mean, in reality, that's never really worth your time to sketch these things by hand. So let's do the first thing that we always do when we introduce new objects. So here's a bunch of vector fields, 8 of them, I guess, and then here's the potential functions for them. I shouldn't say potential, because potential will have another meaning in a second. But here's the functions that those correspond to. So I'm going to leave the graph of these up here. I'll put the functions up on the board, and we just want to do the same thing we always do, right? Match them up with the right ones. And I'll give you a few minutes to try to figure out which ones are which. And then we can talk about that. And again, you don't have to, you know, don't do any crazy reasoning. Just look for sort of interesting things in a vector field that you can pull out. So I'm leaving off the negative, or the f of xy here. These are all f of xy. Okay, so take a minute, try to match up the vectors with the corresponding function, the vector fields with the corresponding function, and well, think about why those things are happening, and then we'll talk about it. And I'll say, you know, look for interesting things, right? Maybe this isn't all that interesting, but all the vectors are horizontal. So what's that true about their y values here? The y value of those vectors will all be 0, right? So you can look at examples where along here y will be 0, but maybe that's not all that helpful because you got a bunch of examples where that's probably true. But that might be, you know, as opposed to this one where you have that vertical line. So think about things like that. Think about these two both have basically the same vector, right? In every place, it's just moved around, and so those ones should correspond with constants. And figure out those two, and so plug away at it. So, any answers so far?
For 19, number 1.
19, number 1. Where did you get that?
Minus y. The x goes to minus y and the y goes to x. So the direction will be down and right.
But so take for instance, this guy at, oh, sorry, better than this guy. Take for instance this guy at 1, 0. What's the vector that should come up?
Minus 1, 0,
0, 1, right? You plug in, so you get 0, 1. Is that a vector in 1 up there? I don't think so, right? You gotta be a little bit careful. So let me say what I said again, right? 1 and 6. That's the same vector in every spot, right? Just moved over. So those should correspond to constants. And again, there's no units given, but this one should have positive x and negative y, right? Because you're moving over, and then you're moving down, and it looks like the x is bigger than the y, so
18.
so that's 18. Does that make sense? You got positive x value, negative y values, and they're constant. So this one should be 1. And then the same reasoning, I think this guy should be 6. Is that okay? Right, and let's just double check. It looks like you're going over 1, negative x, and then up 2, right? And all those vectors.
And 23 will be 2.
Okay, so why is that?
Because the x starts from 1 and the y is everywhere.
Okay, so 22 you said?
23.
23. You think this is 2? All right, let's look at it first. So fixed x's of 1, right? So every x is going to be of length 1. Does that look right? It looks like, to me, those x's are stretching, right? Getting bigger, so I don't think that's right. So I think for this one, all your vectors should be of the same length. And then as you get higher, as your y gets bigger, your y values just grow, right? So at a fixed height, right, if y is 6, no matter what x is, your vector is 1, 6, right? So horizontally, you should get the same vector at every horizontal level for this guy. Which one is that? 3? I lost it. Yeah, I think that looks right, right? Horizontally, you get the same vector no matter what, and let's just make sure, right here we get, up here we have positive x, positive y, so when y is positive, that's right, and then down here you get positive x, negative y, right? So I think that looks good. That one should be 3. Kind of the same reasoning here, right? The 1's fixed, so how is this one going to be? You're going to have constants when you look at them vertically now, right? And so which one has that?
7.
7. So this one should correspond to 7. Again, you can double check a little more. And so now it's really just a matter of dealing with the ones with x's and y's in them, right? And so, I mean, you could do this in a bunch of different ways, but let's do it this way. First quadrant, where are these vectors going to be pointing? X will be positive, Y will be positive, right? So they'll be pointing to the upper right. How about in the second quadrant? X is negative, Y is positive, right? So they should be pointing this way. Third quadrant, they're both negative, they should be pointing, I'm losing myself, that way. Fourth quadrant, X positive, Y negative, that way. So they should be pointing away from the origin every time. Which one's that? That's 2. And again, this is definitely not the only way to reason this out, but I think this is a nice example. Okay, how about, let's look at 21, then everything's negative, right? So if you're in the first quadrant, your x's should be negative, your y's should be negative, so you should be pointing this way. If you're in the fourth quadrant, your x's are positive, so that it becomes negative, and then y is negative, but you're already down negative, so it'll be this way, right? So I think if you just reason that out a little more, they'll all be pointing at the origin, right? So which one's that? 8. Is that okay? And then you have 2 left. How do you decide the difference?
19 is 5 and 20 is 4.
Okay. How do you decide that?
Just put a number in.
Okay.
Put 1 and 1 and it points out.
Sure.
There.
So if nothing else, just plug in 1, 1, and what do you get? Negative 1, 1, right? And so that means you're up at 1, 1, and so do you have negative and negative? Oh wait, that one's negative x, positive y, right?
Yep, so
Which is the upper right one, not this circular one. Does that make sense? So that's 5, and then we're done. That make sense? So same directions as before with these. Just take a fresh look at this in a few hours or tomorrow. Try these again. I think I won't bother with the 3D ones, but it's the same kind of ideas, right? You just think about how those vectors look. So like for instance, these guys, they're all pointing in one direction. They only are pointing in that x direction, right? So your y's and your z's look like they're going to be 0 everywhere, right? And so if you flick down, there's it's this last one, right? You got zeros there. And then, there's a lot of zeros in these ones to help you out. So play around with that when you get a chance. Much more interested in the 2D version just because it's a lot easier to visualize. So make sure you can do that. Try that and ask questions if you have trouble with it. But really make sure you nail down the 2D stuff. Okay. Good. Let's move on here. Let me just jump into this. Recall the gradient of xy is, so you had this function that we called the gradient. Remember, it's this little upside down triangle f. So that's the nabla, I guess that's the letter that is nabla. This is often called the del operator. So you'll see both things. We're just going to read it, the gradient of f. Okay? So the gradient of f is a vector valued function. We didn't call it that back. I should say it's a vector field. We didn't call it that back in Calc 2, but now that we have that terminology, we get this. And if there was a function of 3 variables, you just throw in the f sub z of xy at the end, right? Okay, and so let's just practice and do a couple. Find the gradient of f. Now let's just do f of x equal to x squared sine of x plus y. just a partial derivatives problem. Might have been a little while since you've thought of partial derivatives, though. What's f sub x going to be?
2x
Yeah, I like that.
times sine
Times sine.
plus
X plus
x
y.
equals sine.
Okay, good. So product rule, right? So 2x and then sine, 2x, sine of x plus y, right? And then plus x squared times the derivative of sine of x plus y, which is just cosine of x plus y, and that's it, right? Comma, derivative with respect to y, x squared sits there, cosine x plus y, okay? So it's going to be, the gradient has a lot of properties, and you might have seen this before. We're going to come at it from a slightly different direction, but it's going to be really important to know if a given vector field is really the gradient of some other vector field, and if it is, we can do all kinds of nice, play all kinds of nice tricks on it. But we'll come to that as we move along here. All right, these directions are not all that clear. So what I want us to do is sketch some level curves and then some gradients. And I just say some gradients. You'll see what I mean in a second. So what were level curves? How did you come up with, what was a level curve for a function? Anybody remember? So if you had a function, you could set c equal to f of xy. If you think of like a topographic map, right? Maps of land will often have lines in them representing a fixed altitude, right? If you have a mountain, this mountain, that is the best mountain ever drawn. You might have a two-dimensional map, right, that shows, you know, you got that peak up there, and it's got all these spiraling things down showing you how steep it is at each point. Does that make sense? So that's all level curves are. They're just the lines corresponding to a fixed height of your function. Okay? So we have this function of two variables. Let's not worry about exactly what it looks like, but we have level curves that correspond to the various heights. Okay? And so if we just plug in 0, we get what? 0 equals x plus y squared. So what is that curve? X equals negative y squared. And so I think I'll squeeze in the, it's happening again. So let's just draw this level curve. So what's x equal y squared look like? Parabola on its side like that. Okay, everybody? How about when c is 1? 1 equals x plus y squared, so x is 1 minus y squared. Still just a parabola on its side up here like this, right? That makes sense? And then finally, actually let's make it more interesting. Let's switch to 4 just so we get nice values here. C equals 4. 4 equals x plus y squared, so x is 4 minus y squared. So again, we're over here at 4. 2 there. So these things are all growing. They're going to get a little closer together as you move up. But I'm not too worried about drawing these things perfectly. What's the gradient of this f?
1,
1 comma
2,
2y. Okay. And so a result that you had back in Calc 2, if you remember, the reason that gradient was introduced was to compute directional derivatives. Remember, I don't know if you remember, the d sub u f at AB was the gradient of f dotted with u. And so you use this here, and the point was the gradient always pointed in your direction of maximum increase. Okay, and so the gradient was valuable for that reason. We're going to use it for slightly different reasons. But one of the things you mentioned then was that the gradient was always perpendicular to level curves. And so let's just see that with a couple examples. So what's the gradient at 0, 0? 1, 0. And so if I go and I draw that in here, again, I'm just going to draw them with the full length. I get that vector right there, right? Pointing against here. What's another point on this curve? What point is this?
It's 1, 0. 0, 1.
0, 1. So if I do the gradient at 0, 1, what do I get?
1, 2.
1, 2. So you can see here I go over 1 and up 2. Again, without having some help, it's hard to really draw those perfectly, but that's going to be perpendicular to that curve. Let's just do the gradient at 0, negative 2. So what would that one be? 1, negative 4. And so that would be this point down here, right? And again, it would be over 1 and then down 4. Don't worry about exactly where it is, but it's going to be always perpendicular to this. That make sense? Go ahead.
I don't understand how we can make the direction for the gradient 1.2.
1 comma 2.
Yes.
So when we plug in this point,
0, 1.
this is going in for x, this goes in for y, right? Into here.
Oh.
So it's just 1 every time, and then 2 times y. So if I plug in 1, I get 2.
But when we sketch it, how we know the direction is going?
Right, so it's the vector 1, 2, which means 1 x unit, 2 y units up.
Mm-hmm.
So 1 positive x, oh, I went over too far there. And then, so 1 positive x, and then 2 positive y. So you're pointing up like that. Does that make sense? And then, similarly here, you plug that in, you get 1 positive x, and then negative 4y, so we move down. Is that okay? All right. So we need to talk about what it means to be a conservative vector field and potential functions, and then we got to introduce the curl and some other stuff. I think I'm going to hold off from that, though. We'll do that next time. So why don't we stop there?